My friends, today we are going to see about the IEEE 802.11 communications. The Institute of Electrical and Electronic Engineers is a global professional society with more than 3,95,000 members. To the networking professional, IEEE means to create the standards which we use for communication. The IEEE 802.3 was responsible for creating the LAN standards, and IEEE 802.11 group was responsible for creating the WLAN standard. These 11, these 3, these are all nothing but this was the third group which developed the standards, and this was the 11th group which developed the WLAN standard. So it was named as IEEE 802.11. The original IEEE standard was published in June 1997 as IEEE 802.11 1997 standard, which is often referred to as IEEE 802.11 prime. The latest standard which was iterated and approved and which we are following right now is 802.11 2007 standard. The physical layer specifications. IEEE specifically defines 802.11 technologies at the physical layer and the MAC sublayer of the data link layer. By design, the 802.11 standard does not address the upper layers of the OSA. Although there are interactions between the 802.11 MAC sublayer of the data link layer and the upper layers or parameters such as quality of service and so on. The physical task group works with the MAC task group to create these standards. So the physical task group, in order to communicate the data from one system to another system, it used infrared technology, Fhss and DSS. Infrared technology uses a light-based medium, and the implementation was obsolete. Whereas the Fhss and DSS and the extension from the DSS to OFDM and so on, these uses the radio frequencies. So the Fhss, we'll see about Fhss, DSS, HR, DSS and OFDM in detail. So if you take the Fhss, frequency hopping 802.11 radio cards are often called as class 15 radio cards. And similarly, the radio cards which uses the special type of communication which uses DHS as a communication, it uses class 15 radio cards for sending and receiving. So we will see about the compatibility issues, everything in detail. Now let us see about the Fhss. Frequency hopping spread spectrum was used in the original 802.11 standard and provided 1 and 2 Mbps of RF communication using the 2.4 GHz ISM industrial, scientific and medical band for the legacy class 14 radios. The majority of 802.11 complaint legacy Fhss radios were manufactured between 1997 and 1999. The IEEE standard, that is in North America, the 802.11 Fhss would be 79 MHz of frequency from 2.4 GHz to 2.484 GHz. Actually, if it is from 2.4 to 2.483, it will be around 2.484. So leaving the 2.40 and 2.484, it will be around 83 MHz. But if we are using Fhss in 2.4 GHz band, then a maximum of 79 MHz of frequency will be present. For example, if we are using this is the 2.4 GHz band. So if we are using from 2.40 to 2.484, 83 MHz of This thing will be present. This is channel 1, channel 2, channel 3, channel 4, and up to channel 14 it is present. But if we are using FHSS, only we can use up to 2.480. So only 79 megahertz of frequency will be there. So this is a 2.4 is a band, gigahertz is a band, and then the frequencies 1 megahertz, 2 megahertz, 3 megahertz, these are all the frequencies, and these are all the channels which are presented in a frequency. So we'll see about the FHSS in detail. Generally, the way FHSS work is that it transmits data by using a small frequency carrier space and then hops to another small frequency carrier space and then transmit data and then to another frequency and so on. So if you take an example, see this is frequencies. There will be 1 megahertz, 2 megahertz, 3 megahertz, 4 megahertz, 5 megahertz up to 79 megahertz, maximum of 79 megahertz can be used. And FHSS transmit the data by using a small carrier space and then hops to another small frequency carrier space and then transmit data and then to another frequency and so on. So it usually hops between the frequencies and transmit data. See, with the frequency hopping spectrum, the signal is transmitted on different frequencies at a specific interval to spread the signal across a relatively wide range of bands. Okay. See the figure below. More specifically, frequency hopping spectrum transmits data by using a specific frequency for a period of time known as dwell time. This channel 3, this channel 2, this channel 1, it's a dwell time, it's a dwell time, it's a dwell time. For a specific period of time, it transmits in a specific channel. This is called as dwell time. And after this dwell time, after a specific period of time, it hops to some other channel. And after a specific period of time, it hops to some other channel. Each time a dwell time is reached, the system changes to another frequency and continues hopping. So, if you take for example, the dwell time is around a maximum of 400 milliseconds and typically a dwell time is achieved around 100 to 200 milliseconds. Okay. So the dwell time is 100 to 200 milliseconds. Afterwards, the hop time for hopping between this dwell time, this channel to this channel, the hop time is around 200 to 300 microseconds. So here the hop time is the dwell time is 200 to 300 milliseconds, and after 200 to 300 microseconds, again the dwell time 200 to 300 milliseconds, and so on. It will go on like this, like this, like this, like this. For example, the FCC specifies a maximum dwell time of 400 milliseconds per carrier frequency during any 30-second period of time. Okay. Typically, dwell times are around 100 milliseconds and 200 milliseconds. The IEEE 802.11 standard specifies that a hopping sequence must consist of at least 75 frequencies per 1 megahertz. If this is 1 megahertz, there should be 75 hopping 75 frequencies. The hopping sequence must consist of at least 75 frequencies because a maximum of 79 frequencies are allowed. One frequency is 1 megahertz. Because of the standard specifies a maximum of 79 megahertz, the maximum number of hops possible would be 79. With FHSS, hop sequence would consist of 75 hops and a dwell time of 400 milliseconds, and it will take about 30 seconds to complete a hop sequence, and then again it starts. See, for example, within 30 seconds, 75 hoppings will occur, 75 hops will occur, and Japan uses 23, France uses 35, and Spain uses 23, same as Japan. So different types of countries uses different types of hops. So 75 hops should occur within 30 seconds in a 1 megahertz band, and then the dwell time is around 400 milliseconds, and then the hop time is around 200 to 300 microseconds. What is the significance of the dwell time? This is an important question. This is an important question to be answered because FHSS transmissions jumps inside a frequency range of 700 megahertz. A narrowband signal or noise would disrupt only a small range of frequencies and would produce a minimal amount of throughput loss. Right? The interference. We'll talk about it later. Decreasing the dwell time can further reduce the effect of interference. Conversely, because the radio cord is transmitting data during the dwell time, the longer the dwell time, the greater the throughput. If the dwell time is longer, the output also will be, the throughput will be greater. Because for the receiver, if the dwell time is longer, the throughput will be greater, like the DSSS, which uses a full spectrum, not like FHSS frequency. Within 79 megahertz of frequency, it changes. So if there is a noise, it will be reduced, but not a perfect throughput will be uptime. So, and coming to the DSS, direct sequence spectrum, which uses class 15 radios, as I said earlier, with CCK encoding and BSK and DQBSK for modulation. So, the direct sequence spectrum was originally specified in the primary or root 802.11 standards and provide 1 to 2 Mbps of communication using the 2.4 GHz ISM band. Unlike FHSS, when the transmitter jumps between the frequencies, DSS is set to one channel. If it is transmitting, if the sender is transmitting in channel 1, the receiver will also receive in channel 1. Unlike here, channel 1, channel 2, and channel 3. Here it will frequently hop. But here it's fixed to one channel. The data that is being transmitted is spread across the range of frequencies that make up the channel. The process of spreading the data across the channel is called as data encoding. It uses CCK encoding and differential binary phase shift keying and differential quadrature phase shift keying, which is an enhancement to dBPSK, is the modulation view. Basically dBPSK differential binary phase shift keying uses only 0 and 1, whereas differential quadrature phase shift keying uses 0, 0, 0, 1, 1, 0, and 1, 1. It uses CCK encoding, as said before. Okay, now we'll see about this thing. See, this figure shows that FHS and DSS transmissions. If we are transmitting FHS and DSS, it will collide when the FHSS transmitter hops to portion of the operating band occupied by the DSS transmission. Okay, we'll see about this collision. See, here it will collide. See, as defined by the 802.11 prime, the frequency space in which either FHSS or DSS radio cords can transmit is the license-free 2.4 G Industrial Scientific Medical Band, ISM band. So DSSS uses 802.11 radio cords, can transmit in channel subdivided from 2.4 to 2.4835 G. FHSS are transmitted on 1 MHz subcarrier in 2.402 to 2.480 of 79 MHz ISM band. Totally FHSS uses 79 MHz, whereas DSS uses 83 MHz. As simple as that. chances are that you will not be working with the older legacy 8.2.11 equipment because most of the WLAN deployment technology, as defined by the new 8.2.11 amendments, WLAN companies had the choice of manufacturing either Class 14 radios or Class 15 radio cards. Because these spectrum technologies differ, they cannot communicate with each other and often had a hard time of coexisting. The spectrum are analogous like oil and water, they do not mix well. Therefore, it is important to understand that the 802.11 DSSS, Class 15 and Class 14 radios cannot communicate with each other. Here we can see, I mean, we will see that in detail in later. So, if there is a collision, using the time, space, and frequency to isolate the radio, the following coexistence methods may be acceptable. I mean, the spacing method and so on, which can be implemented in Wi-Fi and Bluetooth. So, in the radio compatibilities, speeds, and mainly the radio speeds and compatibilities will be discussed here. So as we can see, the 2.4 GHz band, 4 types of radios are used, and for the 5 GHz band, 3 types of radios are used. 802.11n is both compatible of 2.4 and 5 GHz band. So if we take 2.4, first of all, in 1997, FHSS came. Then FHSS came, it uses Class 14 radios and the data transmission rate was 1 to 2 Mbps. And in the same year, the 802.11, the prime team developed DSSS with 1.1 and 2 Mbps speed. So this is the legacy prime device. And then later, after 2 years, 802.11b was specified by the task group B, which is an extension of DSSS, HRDSSS, which uses Class 18 radios. Class 14, Class 15 is used. You can ask where is Class 16 and 17? It's for infrared. Class 16 is infrared, completely infrared. Okay, and then the 802.11b HRDSS uses Class 18 radios. It uses 1 and 2 DSSS and 5.5 and 11 Mbps. Millions of bits per second Mbps. So here you can see it's an extension from DSSS. So the prime device using DSSS technology instead of FHSS technology is backward compatible with the 802.11b technology. Similarly, the 802.11g, which came in the year 2003, uses Class 19 radios. So it uses a technology ERP, Extended Range Physical. It stands for ERP, DSS, and CCK. Same as we can see, the DSS uses CCK, complementary code keying, and HRDSS uses PBCC, packet binary convolution coding, to encode the data. And OFDM uses simply convolution coding, the binary phase shift keying, quadratic phase shift keying, etc. The DSS is the most common technology which is used today, but as of now, each and every laptop which is arriving today uses 802.11n technology. The attacks which are performed by the backtrack by our Poly Linux users, I mean, we don't need to buy an alpha core to perform these attacks. 802.11n technology is more than enough. 802.11g was ratified in the year 2003, and it uses C19 radios. So it uses ERP DSS for CCK for 1 and 2 Mbps, and 5.5 and 11 Mbps also. So with ERP HRDSS, and ERP DSSS with PBCC. I mean, the PBCC is nothing but the HRDSSS. It uses the it's nothing but the HRDSSS. It uses 22 and 33 Mbps, and ERP OFDM where 6, 12 and 24 Mbps are mandatory, and 9, 18, 36, 48 and 54 Mbps are supported. And 802.11n HC technology is the C20 radio which was ratified in 2009. So as we can see, 802.11g devices which came in 2003 can support so many channels, and it's around 1 to, I mean, the data rate, see the data rate 1 to 5.5 and 11 for DSSS, CCK, and DSS, HRDSS it uses 22 and 33, and OFDM it uses 3 data rates are compulsory, and then 5 data rates are supported. See, the G devices are compatible with G, and then prime DSS devices. So, and similarly, the DSS is vice versa. But if you take the 5 GHz radio, it uses OFDM technology with class 17 radio. So, class 14 is FSSS, class 15 is DSSS in prime, and class 16 is infrared, class 17 is 802.11a OFDM C17 radios, which also came in the year 1919. So after C17 radios only HRDSS C18 radios came in the year 1999. So and these use of 5 GHz range. So now let us see about the 2.4 GHz. Let's see about 2.4 GHz communication. The 2.4G ISM band is 83.5 MHz wide. As I said before, it's 83 MHz wide from 2.4 to 2.4835. So totally leaving the 835 and 2.40, totally around 83.5 MHz is used. As I said before, in 2.4 GHz communication, these are the 4 types of radios used, and I have explained about the backward compatibilities and everything. So as you can see here, in channel 1, it uses 2.401 to 2.423. Channel 2 uses 2.406 to 2.428. So as you can see, the center frequency, channel is around 22 MHz, and the center frequency is 12 MHz. So each channel, channel 1, channel 6, and channel 11, channel 2, channel 7, these are the non-overlapping channels. The channel 1, 6, 11, and then channel 2 it ends here, and then channel 11 it starts here. These both are non-overlapping channels. Similarly, channel 3 and 8, 4, 9, 5 and 10, these are non-overlapping channels. See, between the channel, a 5 channel difference are there. Minimum of 5 channel difference are there. So it's non-overlapping. So different countries use different channels. The 2.412 uses channel 1, 2.437 uses channel 6, and if it is channel 3, it uses 2.422. It uses the center frequency of 2.422, but it's occupied from 2.411 to 2.433. It uses channel 3, and we are using the SSID of channel 3, and we'll see that in later. And in Singapore, it's allowed. So in different countries allow different channels. In US and Canada, the channel 12 is not allowed, whereas in Europe the channel 12 is allowed, channel 13 is allowed, channel 14 is not allowed in US. Canada and Europe. So channels are designated by their center frequency. Each channel is around 22 MHz wide. It is often referred by the center frequency of plus or minus 11 MHz. For example, channel 1 is 2.412 GHz. That is plus or minus 11 MHz, which means the channel 1 spans from 2.401 GHz to 2.423 GHz. So if you take 2412, add minus 11 and plus 11 to it. That is the frequency here. So if you take channel 32422, add minus 11 and plus 11 to here. So that is the frequency here. So it should be also noted that within the 2.4 ISM, the distance between the center frequencies is only 5 MHz. See, like I told, 2477, 2417 and 2422, 2412 and 2417. The distance between the center frequencies 1, 2, 3, 4, 5, and then 6, 7, 8, 9, 10, and then 11. See, 1 and 2, it's 5 MHz. 2 and 3, it's 5 MHz. 3 and 5, it's 5 MHz. 4 and 5, it's 5 MHz. But between 1 and 6, it's different. Now, I'm talking about the center frequencies, and between the side frequencies 1 and 6, 1 ends in 2, 3, and then 6 starts in 2, 6. So the side frequencies is 3. Okay. Okay. It should also be noted that the distance between the center frequencies is only 5 MHz, with an exception of channel 14, leave channel 14. Because each channel is 22 MHz wide, and because of the separation between the center frequency of each channel is only 5 MHz, the channel will have overlapping space. See, channel 1 is overlapped with 2, 3, 4, 5. We'll see the overlapping channels in detail below. So, what exactly classifies the DSS and HRDSS channels as non-overlapping will be also seen here in detail. See, let us say right. For DSS, the adjacent or the non-overlapping channel, if the frequency is greater than or equal to 25 MHz, it's non-overlapping. So if it is less than 30 MHz, then it is overlapping. As I said, for DSS, for channel 1 and 6, 2.412 and 2.437, the distance between the center frequency is 25 MHz. Right? Okay. But as of 802.11 DSSS, the adjacent or non-overlapping should be greater than or equal to 30 MHz. So it is overlapping. So 167 is basically not overlapping, but literally it's overlapping to a little. So as of HRDSS, the 802.11 standard defines HRDSS as if the center frequency is greater than or equal to 25, then it is not at all a problem. So 802.11 B uses HRDSS, and it's greater than or equal to 25. So 1611 are here non-overlapping channels. For EOP adjacent or non-overlapping, that is, the G devices. If it is equal to 25 MHz, then it is non-overlapping. So if it is less than 25 MHz, it is overlapping, and if it is greater than, it is non-adjacent channel. Similarly, for OFDM, the technology is entirely different. It uses only 20 MHz. So as you can see, the progresses DSS 30, HRDSS and it uses 25. OFDM it uses 20. So we have seen about this thing. So now we'll see about the SSID. as I said, our SSID is VP, and then the signal is -44. The channel we are using is 3 and security is WPA 2. See the 802.11 in devices. And then it's using 802.11 G device. So as of now, I am going to plug in my alpha card. See, as you can hear the sound, I'm plugging my alpha card and let's see whether our device is showing or not. Network is just now managed. Ping, it's being connected. The alpha card is going to connect. Wait, let's see. It's connected. You can see the signal strength is 96 and the link quality is 74. And now let's see. Let it get connected. It's not going to be useful because it's showing the SSIDs and the MAC address of the APs. As I said, G is used here and G is used by here. These uses 802.11 N devices. Okay, see here. This is our AP's MAC and this is our rate. The maximum rate is 300. The core channels is 1 network and overlapping is 11 networks, which means we are operating in channel 3. Channel 3 is the center frequency. See here, there are 11, now 12 overlapping channels. 1, 2, 3, 4, 5, 6, 7. I don't exactly count. It's very confusing. So there are 12 overlapping channels or something. See here. Okay. So with this 50 decibel range, there will be overlapping. Even if it is 1, 6 and 11, in this 50 decibel range, there will be overlapping in DSS, literally overlapping, but not in HRDSS and so on, because HRDSS is completely different. And as you can see, for transforming a 30 minutes HD video, it will take about 42 minutes in 802.11b and 10 minutes in B and 44 seconds in 802.11n technology. Now we will see about the OFDM technology. We have seen about the FHSS, DSS and 2.4G, and then 5G. We have seen about FHSS, DSS and HRDSS, everything. We need to see about the OFDM technology and then 5G. So in 5G, as you can see, it's divided into Uni 1, Uni 2 and Uni 3 and extended Uni 2 channels. So as you can see, 1, 2, 3, 4, 1, 2, 3, 4 and 1, 2, 3, 4. Each uniband can use 4 channels, but the uniband 2 uses 8, the extended uniband 2 uses 8 channels. So as you can see in the OFDM, YFDM actually transmitted across 52 separate and closely precise phase frequency, often referred to as subcarriers. The frequency width of each subcarrier is 312.5 kHz. The subcarriers are also transmitted at lower data rates, but because there are so many subcarriers, overall data rates are higher. Also, because of lower subcarrier data rates, delay spread a smaller percentage of the symbol period, which means that the ISI intersymbol interference is less likely to occur. We'll see about ISI in later videos. In other words, the OFDM technology is more resistant to the negative effect of the interference comparing to DHS and FHSS technology. This is the best technology as of now. As of now means when compared to FHSS and DHS, OFDM is literally a good technology, because in FHSS it uses the frequency hopping. Between the 79 MHz frequency is hopping, and then between the dwell time is hopping, so interference will be more when compared to DSS, which uses a complete range of frequencies for transmitting in a specific channel. Whereas in OFDM, see this in this like this one frequency is there, one channel. If we take this as channel 1 consists of 52 separate and closely precise channels, subcarriers you can say. So if a data is being transmitted, it's being transmitted through these 52 subcarriers. So you can see of the less delay and less interference. So the 52 numbered subcarriers are from -26 to +26. And that's of OFDM technologies. And I think we have studied about the overlapping channels and the non-overlapping channels in simple. 802.11 prime devices uses FHSS and DSS. As of DSS is concerned, if the channel is greater than or equal to 30 MHz, the center frequency is greater than or equal to 30 MHz, not the center frequency. If the center frequency is greater than or equal to 30 MHz, then it's non-overlapping. But if it is less than 30 MHz, it is overlapping. In DSS, the 50 decibel will be overlapping. In part 3, somewhat overlapping will be there. Yeah, as you can see, in this 30 decibel range, it will not be overlapping, but in this 50 decibel range, it definitely will be overlapping. That is, in the sideband lobes, it will be overlapping, but in the main band lobe, it will not be overlapping. In HRDSS 802.11b, if it is considered as center frequency, if the spacing between the center frequencies is greater than or equal to 25 MHz, it's non-overlapping. In ERP, the same as HRDSS, but it should be perfectly equal to 25 MHz. If it is less than, it's overlapping, and if it is greater than, it's non-adjacent channels. So OFDM is 20 MHz. And here in FSHS, the dwell time is around 200 to 400 milliseconds, but typically it's 100 to 200 milliseconds. The hop time is around 200 microseconds.